Let's say we have a space curve given by r of t as f of t, g of t, h of t. Well, if we want to talk about derivatives or integrals of this vector-valued function, it's very simple. Everything is done component-wise. So we can write r prime of t, or we can write dr dt. They're the same thing for our purposes. And you get that just by taking the derivative of each component in its place. Very simple. Same thing that goes for integrals. So if you want to integrate r of t dt, you integrate the individual components. So nothing fancy there. Now, r prime in particular has a very interesting geometric interpretation. So r prime is a vector, right? And it's tangent to the curve that's described by r of t. Okay, so for example, if we had a helix, and you picked a value of t here, it's a little difficult to see, but r of t, or r prime of t, would show you the instantaneous direction in which the curve is heading. Sometimes we want to take away the magnitude of that vector and just get a pure direction. So we have capital T, and that's just the tangent vector divided by its magnitude, so it's a unit vector. And then, not surprisingly, we call this the unit tangent vector. So let's say we pick a point t equals t naught. We have a point on the line. We have a point on the curve, r of t0, and we have a tangent, so r prime of t0. Well, together, if you have a point and a vector, you can define a line, and we call this the tangent line at t equals t0. So given that point and that direction, define the line through that point parallel to that vector. That's what we call the tangent line.